Yeah, thank you very much. Thank you everyone for joining this talk. And for those of you who don't know me, my name is Solmaz, and I'm currently an assistant professor at the Earth and Environmental Sciences program on Khorog campus. And I will be moderating today's lecture. So our lecture today is actually the third talk in this series, and we have one more coming up next Friday. So if you can make it to that one, that would be really great too. And we will send out an invitation very soon. And hopefully we will have many more lectures starting next year. So if you really enjoy these talks and would like to participate as a lecturer, please get in touch with me and I will make sure that you are included in our next series. Now, as you may know, our lecture is about 40 minutes long, 40 minutes or so. And then we have about 15 to 20 minutes of questions and answers at the very end. So feel free to hold on to your questions until the end of the lecture, but also you can type in your questions in the chat box if you like. And you can do that anytime during the lecture. And I will do my best to make sure that they get posed at the very end of the lecture. Now, I also kindly ask you to keep your microphones muted during the lecture and only unmute yourself when you have something to say. And with that, super pleased to introduce today's speaker, Professor Mohssen Moazzen. And just to give you a little bit of a background on Mohssen, he completed his PhD at the University of Manchester in United Kingdom in 1999. And this is where he studied contact metamorphic processes, and he focused on the Western Scottish Highlands. Now, following that, he spent about 20 years or so at the University of Tabriz in Iran as a professor of earth sciences. And for those of you who have not been to Tabriz, this is probably one of the nicest places to learn and study geology. Now, while serving at the University of Tabriz, he also served as a research fellow at the University of Potsdam in Germany and University of Wollongong in Australia. And since 2019, he has been with the UCA and is currently serving as a professor and the chair of the Earth and Environmental Sciences program in Khorog. Now, as you see from Mohsen's talk today, his research focuses on evolution of metamorphic processes, mantle petrology, as well as geodynamic and mountain building processes. And he's particularly interested in figuring out where some of the oldest rocks found in northwestern Iran come from and what mountain building processes they're associated with. And today he will explain how he does that and how his research findings can actually help us with reconstructing the history of the landscape we see today in northwestern Iran. And with that, I would like to give the screen to Professor Moazzen. Mohsen, the floor is yours.
Okay, thank you very much, Solmaz. Thank you for arranging for all lecture series, and also thank you for introducing me. Thanks a lot. So as you can see from the first slide, I'm going to talk about Detrital, Zircon, and Rutile Geochronology, Geochemistry, and Provenance of Cambrian sandstones. And then we are going to talk about the geodynamics of the Gondwana land, especially passive margin of the Gondwana land. As Solmaz said, my research interest is mainly on metamorphic rocks and igneous rocks. But here you can see that I am focusing on the sedimentary rocks, especially sandstones from northwest of Iran. Looking at this title, probably it's sort of, I don't know, very technical, but I will try to explain to you these, these terms one by one. So my talk is consisted of two main parts. One is introduction for those friends which are not geologists, and the rest actually is on the specific features of these sandstones and zircons from these sandstones. So with permission from senior scientists here, Professor David Rogers and Professor Roy Seidel, because some of the participants, they are students, and some of them, they are not probably familiar with geology. As I said, I will try to provide some background. Then the main purpose here is not discussing scientific finding here, although it is a part of my talk, but I like to show you what I am working on and how I do my research and what are the interests and methods and analytical procedures, and to find possibly joint interests and to establish collaborations with other colleagues in the university. Okay. So as I said, some background information. First, I will introduce you the plate tectonics. Most of you know that, all of you know that we are living on a very dynamic Earth surface. We have this plate tectonics going on in Earth, and this is the main difference between the Earth and other planets in the solar system. And here you can see a very simple sketch of this plate tectonics. The main driving force for plate tectonics are these convection cells in the mantle. And we have different tectonic features here: trench, mid-oceanic ridge, and all these are in the oceanic crust, and also we have the continental crust. So we have two types of crust: oceanic crust and continental crust. And since the size of Earth is constant, although some people, they are believing in expanding Earth, and there are some theories on expanding Earth, but most scientists, they consider the size of the Earth constant. So when you have this mid-oceanic ridge and formation of new oceanic crust by uprising magma and melting rocks here, so you need to consume this form oceanic crust somewhere in order to keep the size of the Earth constant. And this happens by recycling oceanic materials into the mantle. And this is by a mechanism we call it subduction. And as you can see, oceanic mantle can go beneath the continental crust. Sorry, oceanic crust can go beneath the continental crust in some specific zones. We call them subduction zone, and it will be recycled in the mantle. So, we have this subduction. Here you can see another photo from, or picture from subduction. This is from, you can see the Cercia from Britannica Encyclopedia. As I said, we have this mid-oceanic ridge, the place you produce new oceanic crust. And we have here to the right the continental crust, and we have this subduction zone where oceanic crust can go beneath another oceanic crust, or oceanic crust can go beneath continental crust. All right. By subduction of oceanic crust beneath another oceanic crust, some processes happen here. The main process is adding volatile compounds to mantle here, and this causes melting, partial melting of mantle and formation of these island arcs. This will happen at the other side as well, and adding volatiles from the subducting oceanic crust to the mantle beneath the continental crust, also it will cause some volcanism. We call it as volcanic arc in the continent. So we have island arc in ocean and volcanic arc in the continent. If you consider this continental margin, or the boundary between the continent and the ocean, this continental margin is a specific type of margin. We call it active continental margin. Why it is called active continental margin? Because subduction is going on here, because we have magmatism here and volcanism here, and it's volcanic rocks erupting here. So here is, in terms of magmatism and also in terms of crustal movements, a very active zone. So this margin is called active continental margin. Okay, as I said, this is our introduction. Again, here you can see an oceanic crust subducting beneath the volcan, beneath the continental crust, and we have here the volcanic arc. And this is an active continental margin at the bottom. But to the top, we have again this oceanic crust, and we have the continental crust, but there is no subduction here. So we call this passive continental margin. And we are going to come back to this. And as you see from the topic of the course, Gondwana passive margin. So we are dealing with this continental margin for some specific time and for some specific continents. And we will see this later on. Okay, so these are some introduction to plate tectonics and introduction to different plate tectonic settings or environments, as you can see in this photo here. The other thing I like to talk about is this geological time scale. And I would be very quick on this because I know some of you will get bored and these are repeated for you. And as you can see here, okay, we have this geological time scale. This is from Geological Society of America, and this is the latest one. And some periods and epochs and ages you can see here. Those rocks we are going to study are those at this part of the geological time scale, which is called the Cambrian or early Cambrian and late Proterozoic. So this again explains probably a part of the title, which is Neo-Proterozoic to Cambrian sandstones. So we are talking about passive margin, and we know what is passive margin now. And we are talking about Neo-Proterozoic and Cambrian boundary in the geological time scale, and we know what is the boundary between this Neo-Proterozoic and also Cambrian here. So the rocks, in terms of their age, belong to this period, which is quite old. And you probably can see these ages here, 540 million years, and I'll come back to these ages later on. The other thing I want to introduce to you is a very interesting specific mineral. This is called zircon. Zircon is a very tiny silicate in the rocks. You can see formula of zircon here, which is mainly zirconium silicate. In the photos, this ZR shows zircon. You can see zircon under the microscope in two different lights. And please pay attention to this scale bar here, so you can have an idea about size of the zircon here. So this scale bar is about 100 micron, exactly 100 micron. So this zircon is, the size of the zircon is about 100 micron across. So we are dealing with very, very tiny minerals. One important thing considering zircon is other elements that can substitute for zirconium in zircon structure. And these are thorium and uranium. And both are radioactive elements. It means that they are not stable. They will decay. They will change to other elements which are lighter by passing time. And this is foundation of finding ages in geology. And zircon is one of those minerals having this element. And it is a closed system. It means you cannot add or remove this material from the structure of zircon. So it actually records or freezes the age of formation of the zircon. All right. This is a foundation for or explanation of the uranium, thorium, and lead geochronological method. When you have this radioactive elements in zircon structure, they can change to lighter elements, which is lead. So uranium-238 changes to lead-206, and you can see all this here. And each of them, they have a half time or half life. What it means this is the amount of time you need to change half of uranium-238 to Pb. If you have 100 atoms, for example, this time is needed to change 50 of them to lead-206. Okay, we have this half-time. This is giga-annum here for different isotopic systems. And if you can analyze this zircon, which is something very interesting, and there are very advanced and sophisticated state-of-art analytical methods, you can analyze these zircons, and then you can find proportion of these different radioactive elements or isotopes. And having the half time, you can calculate the age for these zircon grains and for the rock containing zircon or for zircon crystallization type. So this is other thing, and you can see here in the title. So what is zircon? And what is geochronology? These are familiar now. And what is detrital? Detrital means those minerals and those small rock fragments. They are eroded from a source rock. They are transported by river or wind, but mainly by river, to a sedimentary basin, and they changed into a sedimentary rock. And one of the most important sedimentary rocks are group of sandstones, and we have different types of sandstones. Okay. I hope that now this title is not that much old for you, and now you can see what I mean by detrital zircon, geochronology, and Cambrian, and also this Gondwana passive margin. All right. Now we concentrate on what we did. This is a map of Middle East, and you can see exposure of different rocks according to their geological ages. And again, you can see this geological time scale here. We are talking about these very old rocks. Okay, all these red exposures or red ornament here shows Cadmian exposure of the rocks. So you can see we have considerable amount of exposures in Middle East, in Western Turkey, in Northwest Iran, and in Central Iran. And you can see the study area shown by an arrow here. So this is our study area. This is a very general map of Northwest Iran, a part of Northwest Iran here, which we call it East Azerbaijan. And the place we concentrate on and we did our study is this area here. You can see as a square in this map. Having a closer look at this area, you will see different types of rocks in terms of their composition, their lithology, we call, and also the ages. And each ornament and each color here shows different rock types with different ages. And it is the same for this larger map here. The legend is very small here, you cannot read it, but I will show you what they are for this area of interest. All right, here we have, sorry, I have to go back to the previous slide. We have a very nice volcano here. It is called Sahand volcano. Most of the rocks here, they are these volcanic rocks related to this volcanism. This is relatively, not very old, but relatively old volcano. It is not active now. but the rocks are there. And here NGP to all these rocks are mainly volcanic rocks related to this eruption. But there are some other rocks which are very old. This ornament here, this pattern here with these dots and E1, these are those rocks we were interested and we will concentrate on these rocks. And the other rocks, these are younger but older than volcanic rocks. So these are mainly Cretaceous shales, while this ornament shows Cambrian and late Precambrian sandstones, and the sort of light brown rock here shows very recent or quaternary sediments on covering other rock types. And this pink here, they are igneous rocks, which are older than volcanic rocks. Okay, so we are concentrated on this dotted pattern here, which are sandstone, which are old. Here you can see a simplified geological map from this area. And again, because the previous map, it is a very large scale map. It was 1 to 500,000 scale. But this one is larger view from the area. And you can see again different rock types and different ages. I'm not going to discuss all of them, but again, this dotted pattern here shows sandstones, which are our target of study. And these are sequence of different sedimentary rocks from the oldest one to the youngest one. And as I said, we are interested in these Cambrian rocks. And as you can see here, we can see this arcosic sandstone. And I will explain what is an arcosic sandstone later on. All right, and on the map, you can see these are the dip of the layers. Dip of the layers here are to the south, and here are somehow to the north. So we are dealing with the anticline here, and this is a cross section we try to make for this anticline. And here again, you can see sandstones and older rocks, which are mainly shales, and younger rocks covering the sandstone. All right, can you hear me, Solmaz? Because during the previous meeting, we had some problem with this voice disconnection.
Your audio is fine, Mohssen.
Okay, right. If any problem, please let me know, okay?
Sure.
Thank you, thank you. Here you can see exposure of the rocks. This area this is called Galechai Valley, and here we have a river called Galechai River, and you can see exposure of different rock types. This village is called Tajarak village, and here you can see sandstones, which we are going to study, and these are some other Paleozoic rocks, and this Tajarak village is here, and most of the samples I'm going to talk about them, they are coming from vicinity of this small village here. In the field, you can see different relations for different rock types. And these are the sandstones in this figure A. And at the bottom, you can see the shales as a layer, and we have some very old volcanic rocks. This is called rhyolite. And this is not the actually subject we are going to talk today, but I have done studies on this rhyolite as well. I have geochemistry and geochronology, but we are concentrated on this sandstone here. In this photo here, you can see closer view of shale. Shale is a sedimentary rock rich in clay minerals. So you can see this sort of sort of foliation here, and or being like a page of the pages of a book, and other exposure of the rocks are these shades again as intervals with sandstone. So we have sandstone, shade, sandstone, again shade, and sandstone again. So this is very important again in terms of finding the depositional environment. It was a continental environment or shallow marine environment, or it was a deep marine environment. You can work on it using this succession of the different types of sediments. All right, now we are concentrating on these sandstones. As I said, these outcrops are close to this village. Sandstone is usually looking like this. It's the pink arcosic sandstone. And there are traces of bedding. And bedding is layers of detrital or clastic or eroded materials. They sedimented on top of each other during the sedimentation in a sedimentary basin. So as you can see, some beds are like this, other beds are like this. They are cross-cutting, and we call it cross-bedding. So you can see this cross-bedding in the sample here. As I said, most of the sandstones, they have this appearance in the field. But some of them, they have very dark layers. Again, here you can see cross-bedding. Some beds, this is the direction of the bedding, but the overlying bed, they are horizontal. So there is reason for that, and I will explain very briefly what it shows and how it can help us in terms of finding the positional environment. So all these black layers here and these black patches, they're very interesting, very, very interesting. Why? Because first of all, they show this cross-bedding much clearer here. Secondly, they show this sort of, we call it turbiditic turbulence flow in water. So they are not making sometimes very straight and well-defined beds. So this shows that the water current, it was turbulent during the position of these black layers. And because the color are different, they can pick it very easily in the field observations. And these dark layers, they are very rich in heavy minerals. And we will see them under the microscope. Okay, so these are a few samples made from these rocks. These are thin sections, very thin pieces of rock. They are about 20 micron, the thickness of this rock, and they are under the microscope, so light can pass through some of the minerals, but some of the minerals are very dark and cannot have the light passing through. Under the microscope, you can identify minerals by petrographical skills. So this is what we are teaching to our students, and now we have these microscopes, and thanks to Professor David Rogers for ordering all these things, and now we have a good lab. Looking at these minerals, we know by their optical properties what are these minerals. So here you can see zircon, and these are iron oxides, which is called hematite, and there are other minerals, these brown ones, they are rutile, and tourmaline is another nice mineral. If you have large good crystals, it is a precious stone, but here it is very tiny. Again, please pay attention to this scale bar here, so you can see the size of these heavy minerals. So why we call them heavy mineral? Because they are much heavier than other usual rock-forming minerals like feldspars, quartz, and other minerals. All right. Sorry. This is another clear photo from these minerals. The closest city or town to this area is Ajabshir, so I'm calling them Ajabshir sandstone. Again, you can see zircon, rutile, and hematite. And zircon content in these dark layers sometimes is up to 30%, 40% of rock is made from zircon, which is very high concentration. All right, but these are microscopic views from sandstone without these dark layers or the normal sandstone, this one. Okay, if you look at these minerals here, we have some dark minerals. Again, they are oxides. We have lots of quartz mineral, and also we have feldspars. These rocks are rich in feldspar, and the meaning of arcosic sandstone is a sandstone which contains feldspar. And this is again important to explain the origin of these rocks and also the distance they have been transported from the source to the sedimentary basin. And if you have a look at these sandstones, although there are some cements and the grain size probably are not very clear here, but most of the grains, they are angular, they are not rounded. They are not rounded. So we can probably conclude that these grains as detrital, as those grains transported by water, they have not traveled so much from the source to the depositional environment. Okay, what we did, we used these minerals to classify sandstones, and as you can see here, this is quartz content and feldspar content, and this L is actually lithoclast or rock fragments, if you like, in the rocks. So using the minerals, we can classify the sandstone, and these are mainly arcosic to subarcosic sandstone. These are based on mineralogy. And here you can find sort of tectonic or geodynamic relation to the mineralogy of sandstones. And in this diagram to the left, you can see that these are recycled orogenic materials, the sandstones, and they are cratonic, or they are made in continental crust. So these are two conclusions we can make based on the mineralogy of these sandstones. Okay, looking at the chemistry of sandstones, we took samples from the sandstones and we analyzed them in the lab. So you can see chemistry of them. These are some trace elements: thorium, scandium, lanthanum, and these are hafnium, different elements. We are not worried about name of the elements, but using these diagrams, you can see that sandstones, they show continental signature. And here they are mostly related to upper continental crust, and they are related to passive margin. Now we know that what is the meaning of passive margin, because we already saw that. In this diagram, probably this diagram is not much discriminative for sandstones, but we can see later on that we can use other more discriminative criteria to find out where the sandstones they fall. Here you see some major oxides: aluminum oxides, silicium oxides, magnesium and iron. And on these diagrams or samples, they are in this diagram, they are mainly showing a passive continental affinity, but in this diagram they are scattered in the diagram and it is not very clear. So probably we need other measures to find the nature of the sandstones. Here you can see that they are related mainly to passive margin. Okay, using this diagram, we probably can conclude that they are mainly showing affinity to passive continental margins. And this is sandstone Khorog geochemistry again, and you can see major oxides in the diagram to the top and trace elements in the diagram to the bottom. And these are compared with these passive margin samples from the literature. If you don't consider these peaks, which are for those heavy mineral rich parts of the sandstone, and if you consider only the ordinary sandstone, you can see that there is a very good match between this thick line and other lines for our samples, and also this one. So this is probably, again, another feature that may confirm a passive continental margin tectonic setting for our sandstones. Okay, and zircon. You saw zircon under the microscope, but these are zircons under other type of light, which is called cathodoluminescence light. And these are cathodoluminescent images from the zircons. And these are zircons, we separated them from the heavy mineral rich part of the sandstone. And it was not hard work. For other rocks, you usually have a very hard time to separate zircons. But here, because as I said, about 30% of the minerals, heavy minerals, are zircon, so we were very easily they were separated. And these are zircons. The zircons are cut, polished, and you can see these images under the cathodoluminescence light. And as you can see, we can see these zonings for the zircon, like onions. There are different layers for the zircons. And each layer is formed during addition of materials to this crystallization site. Some of the sources are clearly different from the outer parts. And again, this is important feature for zircons, not these zircons, but many zircons people they study. Again, please pay attention to this scale bar so you can see we are working with very tiny minerals. So this is another image for zircon separates from the sandstones. And here, some of them, they are lacking these cores. Some of them still they have this cores, some of them they are lacking cores. And we will see what it means later on. All right, we analyze these zircons for different things. One, we analyze them for thorium, uranium, and lead isotopes. And also, we analyze these zircons for the trace elements. And as you can see here, these are diagrams showing the zircon chemistry. And deuterium, uranium, or other elements, I'm not going to read all of them, but you can see that in all these diagrams, zircons, they show affinity to granitoids and tonalites. So the source rock, before erosion, before releasing these zircons from those rocks as detrital grains, they were granitoid rocks, or granodiorite and tonalite. And here again, you can see that other diagrams also confirm this granitoid composition for the original rock, zircon crystallizing them, and also continental granitoids. So they are showing affinities to continental granite. So using zircon geochemistry and also whole rock sandstone geochemistry, we can conclude that they are zircons from continental crust and more likely from a passive continental margin or within crust, within plate tectonic setting. All right. Here I'm showing a calculation I did recently on some of these zircons. I'm still working on this data, and I hope to be able to finish this as a paper. And here you can see the ratio of lead and uranium isotopes in our analyzed zircons, and here you can see the age. The calculated age is 563 plus minus 11 million years. 563 million years with this error bar. All right. And if you look at these zircons, we have different population for the ages. We have some very old ages, 1.1 billion year, and those ages which are, as I showed here, around 560 million years. The old ages, they are coming from the interior core of the zircons, and because they are called inherited ages, not crystallization ages, so we consider only the new ages in this diagram, which are Neo-Proterozoic, and they are, you can remember the geological time scale. Again, here you can see the zircon and rutile geochemistry, and comparing zircon geochemistry to granitoids, it shows a very good match. And also here you can see the thorium and uranium content for these zircons, and you can see Paleoproterozoic zircons and Neo-Proterozoic zircon, and you can see that, okay, most of them, they are actually showing this ratio between thorium and uranium. We can use it for further studies in terms of, origin for the zircons. For rutiles, you saw some rutile grains. We have these chemical compositions. It is not very clear, but apparently they are related to metamorphic rocks. So rutiles, probably they are coming from an original source, which was metamorphic rock. I have to be a bit quicker. In this slide, you see southern mass lands. They connected to each other as a large continent called Gondwana land, and it is about 600 million years ago. And you can see the study area here was a part of Gondwana land 600 million years ago. Now, these lands are separated because of continental drift, and they migrated to different parts in the current globe. Okay, in this photo, in this figure, you can see a continental crust. This continental crust is a passive continental margin. Why? Because we don't have any subduction here. So, considering all chemistry and zircon chemistry, we now can say that we had a shallow sedimentation or precipitation basin. Why shallow? Because we can see this cross beddings, and also we can see this turbidity structure in the dark layers of heavy minerals. So the basin was not deep, and the materials, they were provided from a continental crust in a passive continental margin. They deposited and they made our sandstones. But this was not the case for Gondwana land, and we have this Proto-Tethys Ocean and Gondwana land, and this passive continental margin, it changed to an active continental margin by initiation of subduction of the oceanic crust beneath this continental crust. And this shows initiation of subduction of the oceanic crust beneath the continental crust. It was 535 million years ago, approximately. And this is from Zhang et al. And by subduction, then we can have this active continental margin now, and we can have these volcanic activities here, which are as volcanic arc, and this is something which happened later after the deposition of the sandstone. So the position of the studded sandstone occurred at 545 million years ago, because according to the stratigraphy, I mean the sequence of the sedimentary rocks, they are Cambrian in age, early Cambrian. So this is the age, and this is the age for initiation of the subduction of 535 million years ago. So initiation of subduction was about 10 million years ago after the position of these sandstones. And then what happened later on, this is interesting. Here you can see some parts separated from this Gondwana land and other mass lands. They are separating now, Australia, Antarctica, India. They are drifting away from the mainland. And this green line with this triangle shows this subduction front of the oceanic crust or Proto-Tethys oceanic crust beneath the Gondwana land, northern Gondwana, now active continental margin. Later on, all these drafted small land masses, Turkey, Anatolia, Iran, and other parts, they drifted away from this mass and they traveled northward and they actually attached to other mass lands which are not actually the subject of this talk, but I wanted to show you that these are lands which are separated from original Gondwana land. So most of the studies for Gondwana, especially this northern margin of the Gondwana, they are dealing with this stage, with subduction and with active continental margin. But our findings and our studies shows the stage when the margin was passive continental margin before changing into an active continental margin. And this is something new, and there are only a few or only one study showing this very old history of passive continental margin for northern Gondwana, and our study will add to this understanding. So sandstones, they contain heavy minerals, and these heavy minerals are important in terms of having lots of zircon. Zircon ages shows that, and chemistry shows that sandstones, they deposited in a passive continental margin before initiation of subduction and changing it into a active continental margin. Sorry, it was a bit long and I really apologize for that.
Thank you very much, Mohssen, for this wonderful talk. And I'm sure there was a lot of new concepts and terminologies for many of the participants here, but you did a great job of going through every one of them and explaining. And we do have some questions already in the chat box, so I will go over those questions first, and then anyone who has a question, please just raise your hand or unmute yourself and you can ask Mohsen directly. And I guess the first question comes from Gol Morad. Gol Morad, would you like to pose that question to Mohsen yourself? Okay, so I can just read it. So it says, did you find TiO2 for the place of samples? Because I think Gol Morad saw it for one line in one of your diagrams.
You mean in Geochemistry, TiO2 content? Or you are talking about mineralogy?
Hello, I am Gulmurad. Yes, I saw a graphic. Could you please turn back?
Okay, I go to the
chemical composition maybe or something. Yeah.
Chemical composition.
Yeah, it was. No.
This one probably. Yes.
No, later.
So
no, it was not diagram. It was graph. Oh, here, yeah. Titanium O2. So it is a sample 1, 2, 3, 4, 5, 6. Yeah. Or what's the meaning of numbers of?
Yeah. Numbers here they are samples.
Samples.
These are
only,
number 1,
only,
2, 3, 4, 5, 6. Yes, these are my samples.
So as I understand, it is only one sample shows that titanium O2 is increasing.
No. These are 6 different samples. But Gulmurad, the important thing I just mentioned is that some of them, they show these peaks for titanium, for manganese, for iron, and these are those samples.
It's fluctuation. You have no errors there. So.
And the y-axis is a logarithmic axis. So you know that those samples rich in heavy minerals, they are very rich in titanium.
Okay, great. I guess the next question is from one of our students, Saif. Saif, do you want to pose that question yourself?
Yeah, sure. I think firstly, thank you so much, Mr. Mohssen. I think that was easily breakdown, and I think we can definitely relate what Solmaz is teaching us now, a lot of learnings. I just had a quick question on, are there any specific conditions for zircon to crystallize? Like in terms of temperature and pressure, if you can shed some light on that.
Okay, thank you very much for a very interesting question. In terms of temperature, zircon is stable over a wide range of temperature. So you can find zircon in gabbroic rocks. They're crystallizing at temperature in order of 900 degrees of centigrade or something like that. And you can find zircon in granitic rocks. They are crystallizing at temperatures of 650 or 500 degrees of centigrade. So in terms of temperature, no, it is not restriction for zircon crystallization. But as you know, in order to crystallize zircon, we need this chemistry. We need silicium and we need zirconium. And you know that at very early stages of crystallization of magma, when we have very mafic rocks, I'm not talking about ultramafic rocks, but very mafic rocks, because the system, the magmatic system, is not saturated enough regarding zirconium and silicium, so you cannot crystallize zircon in very mafic rocks. You may do, but just probably a few very small zircons. As fractional crystallization proceeds, then you will have a system, a magmatic system, more saturated in zirconium and more saturated in silica content. Then you can get more zircons and sometimes relatively larger zircons. So that's why it is much easier to find and separate zircons from a granite compared to a gabbro. So we have two different issues. One is pressure and temperature. They are not much, defining zircon crystallization, and we have the saturation or activity of different chemical species in the system, which is more efficient in crystallizing zircon and having zircon in different rocks. Did I answer your question, sir?
Yes, absolutely. Thank you so much, Dr. Mohssen.
Thank you.
We also have a question from Zulfagar. Zulfagar, would you like to pose your question?
Yes, thank you. Hello, Dr. Mohssen. How are you? Good?
Hello, Zulfagar. Thanks a lot.
So I have a question about this current graph, about the passive margin and all the 6 samples which you graphed. So as you mentioned, the correlation is very strong, excluding the peaks. I was just wondering about the ferrum oxide. So
about what? Sorry, could you speak
on this graph about the ferrum oxide?
Okay.
So here, your samples kind of are increasing at that part, but for the passive margin is decreasing. I was wondering why in this part, it's opposite directions, the movement.
Okay, you are talking about iron, yeah?
Yes.
Yeah. These passive margin samples, they are from literature, as I said. And all samples, they are from those samples I collected from the field. Okay. But although we are having a sort of normal sandstones, I go back to this field image. You see here, This is sort of normal sandstone, okay? But still in this sandstone, you can see this sort of slightly darker lines or patches or areas. It means that this sandstone, this specific sandstone sample, although you cannot see these heavy mineral enriched layers, but whole sandstone is rich in iron oxides and heavy minerals compared to a normal passive continental margin sandstone. And this is something doing with the source materials. And as you saw in one of these graphs, and I didn't explain it totally, but I can explain it now since you're asking this question. Okay, yeah. Here you can see this chemistry for rutile. And we can say, okay, rutile comes from metamorphic rocks. But here you can see metamorphic rocks, and here you can see metaphyletic rocks. What is the metamorphic rock? Metamorphic rock is a igneous rock which is metamorphosed by, but with high concentration of iron and magnesium because it's metamorphic rock. And here you can see the metamorphic facies. Because you are not familiar with these terms, I can talk about this amphibolite-facies. So a mafic rock which is metamorphosed in amphibolite-facies. Some of the materials for sandstone, they are provided from these metamorphic rocks from a continental origin. And because of that, for this specific sandstone, we have higher contents of iron, as you mentioned here, compared to a typical passive margin sandstone. Okay, Zulfikar?
Yes, that's clear now. Thank you.
I see Khaled Nazar has his hand up, so the floor is yours.
Oh my God.
Yes, thank you very much, Dr. Mohssen, for an interesting lecture. I have one question regarding your graph. The graph, it's an interesting graph, a diagram, which is a kind of spiral diagram. You mentioned that you received these results recently. Could you please go to that one and explain a little bit? I mean that from math perspective, that's an interesting. It's on the top. Just scroll it up. No, not that one. Next, yeah. Not this one. No. Yes, this one. Yeah.
This one?
Yeah. No. The previous one.
This one?
No. Sorry, you passed. Oh, this one. Yes.
Okay.
Yeah.
I go from. Oh, sorry. You're meaning this one.
Yes, this one.
Okay. But you want me to explain about this?
Yeah. What are these lines? Three different lines, and how? What does they explain? That's interesting.
I just want to provide you a very short explanation for this. And if you remember this slide I showed you before, it was on uranium lead geochronological method. Okay, you can have uranium 238 changing to lead 206, and this is the half-life. And as I said, if you can measure concentration of these two isotopes having the half-time or half-life, you can calculate the age. But sometimes you have some problems with using only one of them, only uranium 238 to lead 206 system, we call it, or only thorium 232 to lead 208. Because although we consider zircon as a closed system, and we say that all lead in zircon, isotopic lead, I mean the radiogenic isotopic lead, is a result of these decay reactions. So we are not adding something from outside to the zircon. We are not adding anything out from outside to the zircon, and we are not taking anything out of the zircon. So this is the closed system. And this is the basis of geochronology, finding the ages, okay? But as I said, using only one of them, you can calculate the age. But sometimes you don't trust these ages because you get an age from the first one and you get another age from the second one. Sometimes they're different. So what scientists they do, they combine these two different methods into a calculation scheme, and this graph you can see here. Okay, so now we have different isotopes. We have lead 207 and lead 206 and uranium, different uraniums and different leads. Okay, we have lines here. This line, it is called isochron. And again, I don't know, shall I explain what is isochron in details? No problem. If you have, these ratios exactly the same, they will plot on this actually lines, and I'm not showing the whole isochron here, but what about your samples, our samples? Each of these different loops here, red one, blue one, purple one, it shows analysis for one spot from a zircon sample, all right? And these are error bars. If no error, they would be a spot on this diagram, okay? And then making an average from this and also taking into account these errors, we can calculate the age more precisely, but also, again, here, we don't have spots here. We have all these oval-shaped fields. And as I said, access for this shows the error bars. Smaller the shapes, so more precise, you get the age. And that's why we call it Concordia age. And this is the age, but plus minus 11. And this plus minus 11 comes from these errors, or the average errors for all these small zircons. They are analyzed, and these uncertainties for this analysis. And as I said, yeah, I'm working on them because I have lots of analysis and lots of ratios for my zircon. These are just for a few. And if I do more, I can be more sort of confident that this is the age for my samples. And how we draw this, yeah, you have this ratio for our sample and this ratio for another sample, and you have this minus plus for different errors. It is either analytical error or this is error due to the analytical method you use. These are by laser ablation ICP-MS. If you use another method, so the errors will be different, and we call it errors in this diagram. So I can explain details, but probably we won't have enough time to go through all details. And nowadays, there are several different computer programs. You have your analysis, these ratios from zircon analyzed, and then you can make these graphs in terms of proportion of different isotopes in the zircon samples. Okay.
Okay, thanks, Mohssen, for your answer. I see that we have a couple of more questions, and I also noticed that we are past 2 o'clock, well, 2 o'clock Germany time. So for those of you who need to leave, please feel free to do that. But for those of you who are interested and want to also hear other people's questions, you're more than welcome to stay a little bit longer. I see Polywoon has the hand up, so could you please pose your question?
Yes. Hello, Dr. Mohssen. Thank you for the presentation.
You're welcome.
So I was wondering that the crystal in the beginning were they were angular and immature, so there was no physical weathering. But since it's around 500 million years old, so was there any chemical weathering or any chemical alteration in zircon?
Okay. Looking at this photo in the title of the talk, you can see zircons are sort of rounded. So we have physical erosion for the, or physical alteration erosion for the zircon. But about the chemical ones, in zircon or zirconology, we call it, we consider zircon as a closed system. You can find other minerals containing uranium, lead, but why we are not using those minerals? Because in terms of structures, as you know, zircon is a tectosilicate and it has a very closed packed crystallographical structure. And you know that this type of structure is very resistant. So we just consider zircon as a closed system. So we don't consider much chemical alteration, or in other terms, addition or reduction of some materials from zircon structure. But I didn't bring other data here. You can check if zircon was an open system or not. And how you can do that? You know that from these different isotopes for lead, we have one lead isotope which is not radiogenic, and it is lead-2O5. So the amount of this lead won't be changed by these decay reactions. So you can check the lead content of your samples against the non-radiogenic lead, which is lead-2O5. And this is a method that you can probably sort of check the chemical changes to your zircon grains. And if you can see a real problem there, then the ages you are estimating probably are not very reliable ages. And again, I don't have this slides here, and I want to go through the details, but we know that we can do it. We can check the chemical alteration for zircon, but in overall, zircon is considered as a mineral which doesn't experience much chemical alteration.
Okay, thank you.
Guess the next question is from Mish, and after that, David, you can go.
Thank you very much, Dr. Moazzen, for such a fruitful presentation. So I just have a general question regarding the, what's the main difference between zircon and zirconia and diamond, as zirconia is comes closer to resembling diamond than any other natural gems as well. Also the hardness is very close to diamond. So what could be the main difference between these two gems? Thank you.
I mean in hand specimen, or how we can distinguish zircon from diamond? Is it the question?
Yeah, the main difference between these two gems. Yeah. Because there are lots of, zircon is also sort of resembling this, resembling diamond in many categories. For example, the hardness is also closer to diamond than any other gems. So what would be the main difference?
Okay, you can have crystallographical shape, because crystallographical shape for diamond and for zircon, they are different. And also, as you said, although the hardness, they are close, but they are not same. And we know that in this real hardness, diamond is much, much harder than chrome, which with hardness of 9, and much harder than zircon. So hardness and crystal shape, these are two different features. Probably you can distinguish diamond from zircon. The other thing would be the luster. of two different minerals, and also probably you can look at, I don't know, other different crystal defects, which these crystal defects, they obey the main crystallographical system of the two crystals, and defects will be different in diamond and zircon. So there are several methods that you can distinguish zircon from diamond. But if they are sort of detrital and you don't have good, well crystallized grains or crystals of these two crystals, as you said, it is difficult to distinguish these two minerals, and you need a very good expert gemologist to see which one is diamond and which one is zircon. Sorry, I don't have much to add.
Thank you, sir.
David, the floor is yours.
Thanks for a really clear talk. It was easy to follow, and it's really good to see so many of your students here and understanding and asking great questions. That's all really good to see. My question has to do with your tectonic interpretation. As I understand it, you have zircons as young as 560 million years.
Yes.
And then you think your sandstone is 530 million years old. So that just seems like two ages that are very close to one another. So that have you considered that the zircons as young as 560 million years ago were created by some sort of magmatism associated with continental rifting that preceded the passive margin?
Thank you very much, David, for this very interesting question. Yes, we can consider this magmatism somehow coeval or contemporaneous with formation of the basin. So this is something I am working on, and I will use this question to concentrate on this aspect. But as you can see from the sandstone petrography, and as you can see from the sandstone nature, which is arcosic, and also this roundness and the shape of the grains in sandstone. So probably we are not dealing with long process of in terms of distance and in terms of time of these materials being transported. So yes, we can consider sort of rifting and rift magmatism, and at the same place or very close to that, formation of the sedimentary basin, and supplying all these materials for sandstone from this sort of very close in time granitoid or other types of magmatism, but mainly granitoids. I need to work on the tectonic model, and I thank you for this very interesting question. I don't have a very clear answer for that, but this is something that I was thinking about.
Thank you very much. Again, lots of good data, and probably not too many other people have data from this area like this. So it's an important contribution.
Thank you.
Sadaf, you have a question?
Yes. So, Mr. Moazzen, you linked the black marks on the sandstone in one of your. Can you hear me clearly?
Yes, Sadaf.
Okay. So yeah, you linked the black marks in one of your pictures of sandstone to turbidity, or yeah. So I was just wondering if you could elaborate on this link between turbidites and the black marks or the iron formation that is present in the area that you led your research in. So yeah.
Okay. Thank you for this good question, Sadaf. Okay, You can see here two photos from exposures of the sandstone in the field. And as you can see, these black marks, as you call it, and these are parts with heavy mineral concentration, they show these sort of funny structures, which are not due to deformation. They are not folds, okay? Why they are not folds? Because the sandstone itself is not folded. If you look at this first sandstone here and here, there is no deformation. The sandstones are not deformed. But you see here this deformation-looking structures. These are not deformation. So how these structures they form? If you have a turbulent water flow, then you can have these sort of structures only because of processes during the transportation and sedimentation, not because of late deformation. Okay, so this is the meaning of these turbiditic features for these structures. But what is the application? The application is that if you have a very deep depositional margin, you cannot have turbiditic water flow in deep sedimentary basin. So you need to have shallow sedimentary basins in order to have these turbiditic currents. So these are indicative of shallow sedimentation basin. And also, as I explained, and you know this very well, all these cross beddings, also they are confirmation for shallow sedimentary basin. And these are, again, in accordance with a continental margin and more likely a passive continental margin. But as Dave said, probably these margins are brought about by rifting in these rifts, which we can have magmatism very close in age to the position of the sediments, sandstone. Okay, Sarah?
Yes, thank you very much for your answer. And yeah, it was a very informative presentation, and we could connect a lot of things that we studied with Solmaz. So yeah, thank you very much.
Okay.
And two more questions, one by Arslan and then Khalid Nazar, I think.
Arslan, you're first, please.
Thank you, Mr. Khalid Nazar, and thank you, Solmaz. Hello, Dr. Mohsen, and thank you so much for this great lecture. It was very informative indeed. So I was just wondering if like zircons are always associated with passive continental margins only, or do we find them in active passive margins too? I don't know if you already explained this, but I was just wondering that.
Now you can find zircons everywhere in lots of different types of rocks, in sedimentary rocks here, but the origin was a granitic rock. And you can find zircons in active continental margins. And here, go back to this active continental margin, and you have this volcanic arc, which is mainly anthracite in composition. And then when you make the crustal thick enough here, the later pulses of magma probably cannot travel all through these very thickened active continental margin. They will crystallize as plutonic rocks, and you can have zircon both in this volcanic and in this plutonic rocks. So you can have zircon in different types of rocks in different tectonic settings. They are not only restricted to sandstones in passive continental margins. And that's why zircon is so important in studying age of metamorphic processes and metamorphic events. And if you are interested, you just Google this thing I am telling now. Zircons are forever. Okay, just Google this, zircons are forever. Then you will come up with a very nice organized website for zircon studies or zirconology. And then you can find lots of information for zircons in different rocks. And Before Nazar asked this question, I just wanted to add this very interesting aspect. When we were talking about zircon crystallization, answer to another question, I explained that zircon in mafic rocks is very small and very rare. And in peridotites, zircon is even more scarce. You cannot find zircon in peridotites. But now some scientists, they are finding zircons in even peridotites. And I was in contact with the Chinese scientists. They are crushing and they are processing about 1 metric ton, 1,000 kilograms of peridotites. And then they look for zircon and they can separate 2, 3, 4 small grains of zircon from peridotites. So you can see that zircon, they can happen everywhere. Okay?
Thank you, Mr. Moazzen. Thank you so much.
Welcome, you're awesome.
So Khalid Nazar.
Thank you very much. Yeah, my question is in the chat box. Is it possible to create or get the artificial zircon or maybe something closer to this? And then using this opportunity, I'm sorry, I would like to ask another question. Which country has more zircons? And what do you think, why this specific country has more? Is it because of some, I don't know, geological structure or the mountainous area or whatever? And then for your information, I think we have also zircon in Tajikistan. There is a factory of zircon, but I don't know if they're producing zircon or something else. Thanks.
Thank you very much. Yeah, answering the first question, it is virtually possible to make all minerals in the lab. Now scientists in different labs, in universities and research centers in the world, they are making artificial minerals, and they are making zircon, they are making feldspars, quartz, high pressure quartz, and different types of minerals. And they do this not just for fun. They study some minerals which are rare, or even they are not that much exposed in the Earth's surface because they can be found only in middle mantle or transitional zone of mantle or even lower mantle, and they are looking at these phase relations and phase changes. I mean, the mineral changes by very high pressure and temperature we can find probably, say, for example, middle mantle or upper part of the lower mantle. So all these minerals can be made artificially in the lab, including zircon. And for those countries that they have zircon, we are talking about two different types of zircon. One was the question by Mish. Are we talking about very large, relatively large, well-crystallized, beautiful zircons and gemstones? Or we are talking about zircons as very tiny particles, but concentrated in some of the rocks. So India is one of those countries, or there are some other countries, you can find zircon-rich sand, not sandstone, sand. If you go to the beach, you know, the seaside, you can collect some sands and you can see there are enough amount of zircon, and you can process in the science, it is called dressing. You can dress these sediments to separate zircons from these sands. And what is the use of zircon? There are several different usage for zircon. This is a resistant material, and zirconia is very important to making some very important, chemical compounds in electronics, in medicine, in dentistry. So zirconia is very important. And you saw this area I showed before in northwest Azerbaijan. Yeah, we were concentrated on this area next to Tajarak village, but then I looked at all these sandstones here. Why? Because I was interested to find at least a layer of these zircons, not 0.3 millimeters or 1 millimeter, but 1 meter, half a meter, 20 centimeters. but I couldn't find. If you can find such a layer with this high concentration of zircon and other heavy minerals, so it is potentially very valuable and you can use it as a zircon resource. And about Tajikistan, I'm not sure where they are bringing zircon and how they process zircon, what they use this zircon for, but I need to read about it. Yeah, thank you.
Thank you, Professor.
Great, thank you everyone. And I know this is really late, but that shows how much interest is out there. And thank you so much, Mohssen, for taking your time to walk us through your work and also answer all the questions. So if there is no other question, this would be a good time to wrap up. Is there any other question? Anyone wants to say something? This would be the time to unmute yourself and share your thoughts. Yes, I see a hands up. I think this is Khizer, if I'm not mispronouncing the name.
Yeah, it's Khizer, yes. Hello, Molim. Good to hear you.
Hello, Khizer.
Yes, so I just, I asked a couple of questions, but both were answered, already. One was, how, what other dating techniques can be collaborated with zircon dating? It was answered. And then the next one was, if zircon finishes, what happens next? Then you already answered about the artificial. So I'll just ask one last question. If we can produce, if people can produce zircon artificially, what happens to the value of it? Then many people would be able to, just make it in the lab. And then how do you see the value of it declining or, increasing?
Yeah. This is a question you can ask for diamond as well. So people, they are producing artificial gems, artificial diamond with different methods, and sometimes with relatively simple methods. If you remember, and we had this discussion probably, and last year my talk in this lecture series was on diamond. And for producing diamond, you need very high pressure and high temperature, but now they produce VDCs, which is called or vapor deposition or carbon vapor deposition, making diamond only by vaporizing carbon and then deposition of this vapor of carbon into diamond. But you know that not much labs they can do that. You need first science for that and sophisticated equipment for that. So that's why even for some artificial gemstones, the value, although it's much lower than natural ones, but probably now some of them, they are compete in terms of price with natural ones. So it is not like that you are making, I don't know, ice cream, making zircon or diamond. But this is a question, yeah, this is a remaining question we can think about. I probably, as Mish asked the question, I was expecting you asking what is the difference between artificial zircon and the natural zircon. So I don't know how to answer your question in terms of economic value of artificial ones and natural ones, because artificial ones, they need lots of effort to make them. So probably they are not very cheap and they are not very abundant. Okay, Khizer?
Yeah, but the one we found by mining, it's less let's say if lab once there would be a time that it would be more accessible, right? But then the natural zircon will lose its value, or I think it will. I don't know if I'm wrong, but it might finish as well, because it's very rare already, and then it's like billion years old. So I don't know.
Okay, I just use your question to clarify something. It's that it is not the case that all zircons are 500 million years. No. In a crystallizing magma today, you can crystallize zircon. And we have zircons in some of the papers published, and I can share these papers with you. The age of zircon is only 20 million years, not 500 million years. So this is not the case that zircon is only restricted to a specific, very old period of time in the geological time scale. No, this is not the case. So you have zircon, you can crystallize zircon in those magmatic systems. They are active beneath the surface, and even we have zircons, recrystallization in metamorphic systems, and probably even some zircons in sedimentary systems. Not detrital zircons, but neoformed zircons. It is very, very rare. It is difficult to crystallize zircons in sedimentary rocks, but sometimes we can read some papers showing that probably some zircons, they are very late. So, as I said, zircons are not all of them very old, and it won't finish because mantle will supply zirconium to crystallize zircon in magmatic systems which are active, or they will be probably active in the future. I'm talking about geological future in this time scale.
Okay. Yeah, thank you.
Mohssen, I have just a very broad question for you. Do you plan to bring similar research, or are you currently working on similar work in Central Asia? Is it possible to extend this work and do something similar to this in Central Asia?
Yes, thank you for this very good question again. Solmaz, I have several projects in mind, and some of them, they are started. I have sampled several rocks when I was traveling from Khorog to Grand Cheshma and then towards Ishkeshin with Ben and Genevieve and my wife. And then I have some samples from the Dashtubala, these mountains around the campus. And also I have some samples from the way from Khorog to Darwas. Sometimes I ask our dear friends, drivers, to drop me a stop for a very small, quick investigation of the rocks and take some samples. I have them, image references for all these samples, and I have made about now 58 sections from these samples when I was in Iran, and I'm in Iran. And I made a preliminary study on this, and I can see that we have very beautiful zircons in some of these rocks. So this is a project. I discussed this with my research network, and they are very interested in helping me in giving this opportunity for me to be in their lab, to analyze the zircons and whole rocks. And more importantly, I like to get our students involved in this sort of research activities. And I have already invited some students from juniors, because I know that seniors, they will be very busy with their diploma thesis, but I have wrote to a few students from juniors, and I will get them involved in similar researches. Yes, I have some data. I need to finish them in terms of finalizing them as papers. These are mainly from Iran, but I have ongoing works on Central Asia. Thank you so much.
Oh, really great. Yeah, we're looking forward that perhaps maybe your next talk would be focused on samples from Tajikistan or Central Asia. This would be wonderful. And just one last question by Nadara, and I think then we can call it good. Okay. Nadara.
Yeah, thank you so much. Hi, Mr. Mohssen. Thanks for the very fruitful and informative.
Sorry, Nadira, I cannot hear you clearly. Could you talk closer to the mic?
Yeah, can you hear me now? Okay, I think I'll just type a question.
Or you can type your question in the chat box and Solmaz will read it for me.
Yeah, sure.
So as we're waiting for Nadara to type in her question, is there anything else anyone would like to say? Comments, questions, compliments, complaints?
Can I say something? Sorry.
Please.
Yes, it's me, Kholik Nazar. I thank you very much again, Dr. Mohssen. And I was wondering if students have something to share with us next time. I know you guys are working now on your diploma thesis, and maybe you already have something to share with us. So you're most welcome. And then just send it to Solmaz, and you can present your work. Even if it would be just the draft work, that's okay. Am I right, Dr. Mohssen?
Yes, of course. Yes. But still we are waiting for proposals. Defending proposal is a good practice in most of the universities, so we can consider defending the proposal, not the final diploma thesis. So your students, the seniors, they will collect data, they will analyze some literature before they're writing their own diploma thesis, and from this information, I'm sure that they can prepare good talks, at least to introduce their research and their methodology, what are the questions they are looking for, and how they are going to answer these questions, even if they don't have results ready yet. Of course, they don't have. So it is possible, and I support it. Thank you for the concern.